class, today we're going to be talking about section 4.4, which is solving exponential and logarithmic equations. So just a couple review pieces from our last lesson when we talked about exponential functions. An exponential equation is an equation containing a variable in the exponent. So we talked about exponential functions have variables in the exponent. This is kind of the same idea. You can see examples all the way through these notes here. We can solve exponential equations by expressing each side of the equation as a power of the same base. Now, we can't always do this. And when we can't do this, we're going to see what that's like after these examples. But if we can make the two sides of the equation, rewrite them as powers of the same base, then it means we can do these problems without the use of a scientific or graphing calculator or using logarithms. So for example, example 1a, we are going to solve this. If you notice, 16 is 2 to the 4th power. So I can rewrite this as 2 to the 3x minus 8 equals 2 to the 4th. And then if you think about what equals means this side has to match this side. So if the bases are the same, then all I need to make sure is that the exponents end up being the same. So then I can rewrite my equation as just the exponents being equal to each other. So I can figure out what x value will make the exponents the same. So solving, I can add 8 to both sides. I get 3x equals 12 and x equals 4. Now be careful, x isn't 4 because 16 was 2 to the 4th. It just happened to be 4 when we set the two pieces equal to each other. All right, part B is the same idea, just a little different because we have to convert both sides. So 9 is 3 squared and 27 is 3 cubed. So I'm going to rewrite these as 3 cubed to the x plus 3 equals 3 squared to the x minus 1. Now note, a to the, or I'll do this, x to the n to the mth power is x to the n times m. So we have an exponent and then raised to another exponent, we're going to multiply the exponents together. All right, so I'm going to multiply this in, don't forget to distribute, 3 to the 3x plus 9 equals 3 to the 2x minus 2. Now I have the same bases. I can use just the exponents as my equation. 3x plus 9 equals 3x minus 2. Ooh, interesting. I made a mistake when I rewrote this. 2x minus 2. All right, so now I'm going to subtract 2x, and I get x plus 9 equals negative 2. I'm going to subtract 9 from both sides. I get x equals negative 11. Exponential functions themselves have domains of all real numbers. So technically, any x value, as long as we haven't made a mistake, any x value should be fine. We shouldn't have any extraneous solutions or anything. Now, what if we can't write both sides of the equation with the same base? For example, 4 to the x equals 15. 4 is a power of 2, but 15 isn't. So how do we do this? We're going to change to log form. And if you're not sure how to go between exponential and log form, you want to go back and watch one of my previous lessons, which, if I'm not mistaken, was lesson 4.3. Let me look at my notes here. I think, or 4.2, lesson 4.2. All right, so what we're going to do is we're going to change this to log form. So log form of this exponential function, I'm going to write log. The base of the log is the same as the base of the exponent, so it's a base of 4. Of 15 equals x. So remember, the log is the exponent. So the log equals the exponent. Now I can use my calculator to figure out what the log base 4 of 15 is. I'm going to use the change of base formula, which looks like this. X equals log of 15 divided by the log of 4. So again, from our review from our previous lesson, a log without a base showing is an automatic log base 10. And we can use our calculators with a log button. So I'm going to do log of 15 divided by log of 4. And okay, this is pretty low tech here, but make sure that you close the parentheses after the 15 before you type in the other log. Otherwise, it's not going to work out. All right, so we have 1.953 as our answer. All right, so we can do the same thing for part B. I would suggest you try B, pause the video and try it out. Be careful, you cannot divide both sides by 10. I know right now it looks like you really want to, but you can't divide something that has an exponent. All right, so changing to log form, log base 10 of 120,000 equals x. Now log base 10 is already, we don't have to use change of base formula because that's already the log button in our calculator. So we just press the log of 120,000 and we get x equals 5.079. Now example 3 has a little bit more involved before we change to log form. So step 1, we need to isolate the exponential part. And then step 2, we change to log form. So in this case, the part with the exponent isn't isolated. So what I mean by that is I need just this part here to be isolated. So to do that, I want to move things away from it in order of what's least connected. So the -3 is going to be less connected to that exponential piece than the 40. So I'm going to do that first. Oops, so 40 e to the 0.6x equals 240. And then I'm going to divide by 40. Oops. I get e to the 0.6x equals 6. Then I'm going to change to log form. Now a log base e of 6 equals 0.6x. A log base e is the ln. So I'm going to rewrite that as ln of 6 equals 0.6x, because then I can just use one button in my calculator. Divided by 0.6. And x should be, let's see, where are my notes? 2.986. All right, we're gonna do example 4, although if you're in my class right now, I don't think we're gonna be testing on this because it's, well, we're doing distance learning, so we are cutting some stuff out, but I'm gonna use these videos later, so I'm gonna do this example. So if I have an exponential piece on both sides of the equation, it's a little bit more involved. There's a couple ways you can do this. My favorite way is to take the log of both sides. So this is a little different, but it looks like this. Log of 5 to the x minus 2 equals log of 4 to the 2x plus 3. So I just took the equation. I didn't change its form. I just inputted the log on both sides. Think about it this way. If the log of w equals the log of 5, then w would have to equal 5 for those two things to be equal. So I'm kind of going backwards from w equals 5 to log of w equals log of 5. All right, then I can use my exponential power properties of logs, which you can go review and bring these out in front of the log. So I'm going to have x minus 2 times the log of 5 equals 2x plus 3 times the log of 4. So I can only bring those exponents out in front once I convert them to log forms. Now the log of 5 and the log of 4 are just decimals. If you plug the log of 5 in your calculator, you get a decimal. And I know it's hard to see here. So this is the same as x minus 2 times 0.699 and 2x plus 3 times 0.602. And then I can just distribute these in. I know that this is going to be a little bit messy with all these decimals, but it's all right. We are going to end up with, let's see, we have 0.699x minus 1.398 equals 1.204x plus 1.806. I'm going to get my x's together by subtracting 0.699x. I'm going to get the other pieces to the other side of the equation. Oops, 806. Now I have let's see, negative 3.204 equals 0.505x, and x equals negative 6.345. So this is definitely a more advanced problem. So don't worry too much about it if you're in my fall 2020 course, but we will be using this for later courses. All right, so that is how to solve exponential equations. So now let's change gears and look at how to solve log equations. So a logarithmic equation is an equation containing a variable in a log expression. For example, log base 2 of x equals 5 or something. This is a pretty basic example. We can have other pieces happening to it as well. And similarly to what we were doing before, solving exponential equations, we want to change to log form. Solving log equations, we want to change to exponential form. After we isolate the variable, step 1, we want to isolate the log part. And then step 2, we want to change to exponential form. All right, so example 6a, the log is already by itself, so we don't have to really do step 1. What we're going to do is change it to exponential form. So the base of the log, which is 4, is the base of my exponent. The log is the exponent. And if you think about what is in math, it means equals. So the log equals the exponent. So this here is the exponent. So 4 squared equals x plus 3, and then 4 squared is 16 equals x plus 3, and x equals 13. Now, we have a little bit more work to do because the domain of a log is not all real numbers. A log function, if you remember when we graphed functions that were logs, they have a vertical asymptote, and I'm just going to do one without transformations here. So vertical asymptote, and then they look something like this. So y equals the log of x. So this would have a domain of x greater than 0, which means the argument of the log, where that x is in my equation, has to be something greater than 0. So we need to make sure that my answer still holds true for that property. So if I check this, I need to make sure plugging 13 in for the x isn't going to make that argument of the log 0 or negative. So log base 4 of 13 plus 3 equals 2. We're good to go. That's a log base 4 of 16 equals 2, and 4 squared is 16, so that checks out just fine. All right, so part B, our log part isn't isolated yet, so we want to do that first. Divide by 3. So I have the ln of 2x equals 4. Now I can change to log form. Now remember, the ln has a base of e. So it's hidden, but it's there. It has a base of e. So when we change it to exponential form, it would be e to the 4th equals 2x. Now there's a calculator button for e. You might see something like, so in your calc, e to the x is a button which will automatically give you e and then a spot for an exponent, or you can do e and then the button with the little, we call it a caret, but that little thing gives you exponents. So e to the 4th is 54.598, and then divide by 2, and x is 27.299. Again, you want to check that to make sure it doesn't make the log have a negative or a 0 argument. So 3 ln of 27.299 equals 12. And you can actually plug that in your calculator. See if 3 times the ln of 27.299 equals 12. And remember, we rounded that answer, so it might be a little off, but as long as it's really close to 12, you're fine. All right, part C, it's already isolated, so we're going to change to exponential form. 2 to the 3rd equals x plus 20. I have 8 equals x plus 20. Subtract 20, and I have x equals negative 10. Negative 12. Are we allowed to have negative solutions? Well, let's check it. Log base 2 of negative 12 plus 20 equals 3. Well, it's a negative x value, but when I plug it back in, I have a log that's just fine. So yes, we are allowed to have negative solutions. It's just when we plug them in, we're not allowed to have the log of a negative number. So yes, as long as it doesn't make the argument of the log negative or 0. All right, example 7. We have 2 logs being added. So remember, we have a property that we learned, property that says the log base b of m plus the log base b of n equals the log base b of m times n. So we can combine them into one log, which we definitely need to do before changing to exponential form. So log base 2 of x times x minus 7 equals 3. So I'm going to combine those 2 logs into one by using my product rule. I can simplify the inside of this as x squared minus 7x, distributing that x in, and then change to exponential form. 2 to the third equals x squared minus 7x. Now, 2 to the third is 8. X squared minus 7x. Now I have a quadratic equation. In order to solve this, we want to get everything to the same side so that it equals 0, and then see if we can factor, or you can use a quadratic formula. But remember, these are all things we learned from our first unit or 2, so we're bringing all those things back and combining them with what we're doing now. Don't you love how math just builds on itself? All right, I can factor this. 0 equals x minus 8 times x plus 1 are my 2 factors, which means x equals 8 or x equals -1. Now, we have to check our answers. So anytime we start with a log equation, we have to check our answers because the domain isn't all real numbers. We have a restricted domain. Log base 2 of 8 plus the log base 2 of 8 minus 7 equals 3. This should be just fine. The log base 2 of 8 is 3, plus the log base 2 of 1 is 0. Again, if you're not sure why, remember the log is the exponent, and you can go back to our previous lesson and look at that. So x equals 8 is just fine. Now, if I check x equals -1, I get log base 2 of -1 plus log base 2 of -1 minus 7 equals 3. No, this is not okay. Think about it this way. If the log base 2 of -1, if we had that equals something, then 2 to the what power equals -1? You can't take a power of 2 and get -1. Even 2 to like a negative exponent would just make it a fraction. So you can't take a positive base to an exponent and get a negative number. So x can't equal -1. Now be careful, it's not because x is negative. We had x equals -12 in our last example, and it was just fine. It's because after we plug it in, we ended up with a negative argument. So we have x equals 8, x can't equal -1. All right, let's look at one more example. This one's a little different. So we want to start out by doing kind of the same thing. We have a property that we learned, which was the log base b of m, m minus the log base b of n equals the log base b of m divided by n. So anytime you have a negative log, a minus sign in front of the log, it's going to send that argument down into the denominator. So we're going to have ln of x plus 2 divided by 4x plus 3 equals the ln of 1 over x. Now this equation is different. It has an ln of both sides, or a log on both sides of the equation. The other ones didn't. They only had it on one side, and on the other side was just a number. So just kind of think to yourself, if you have the log, or the ln is just a log base e, the log of w equals the log of 5, what does w have to equal? Well, it would have to be 5, which means as long as I have a matching log with a matching base on both sides of the equation, and I've combined them into just one log on each side, I can just get rid of them. They disappear. I don't care about them anymore. They're already equal. I just need the arguments to be equal. So I'm going to drop the ln's, the natural logs, and rewrite it as just the arguments being equal to each other. Now to solve this proportion, we can cross multiply. So I get x times x plus 2. So multiplying this to that and this to that equals, with an equal sign in the middle, 1 times 4x plus 3. I get x squared plus 2x equals 4x plus 3. Subtract these pieces over. X squared minus 2x minus 3 equals 0. Factor x minus 3 times x plus 1 equals 0. And x equals 3 or -1. Now again, we have to check to make sure that these work. So check. If I plug 3 in, is it going to make any of the arguments negative? So ln of 3 plus 2 is fine, minus the ln of 4 times 3 plus 3 is fine, equals the ln of 1 over 3 is fine. This one is just fine. Nothing's negative. If I check the other one, ln of -1 plus 2 is fine. That's going to be +1. Minus the ln of 4 times -1 plus 3. Nope, that's going to be a -1 in there. -4 plus 3 is -1. And ln of 1 over -1 is also a problem. So x can't equal -1 because when we plug it in, it makes the argument negative. And when are we allowed to use this shortcut where we just drop the logs? So this is if we have one log on both sides of an equation, and they do have to have the same base. Okay, so last example here for our notes. We have our compound interest rate formula. I love when we do application problems, especially when they're finance related. It's very fun. So this describes the accumulated value A of a sum of money P, the principal after T years at annual percentage rate R, and decimal form compounded N times a year. So we've gone over this formula before in previous videos. How long will it take $25,000 to grow to $500,000 at 9% annual interest compounded monthly? So as I'm reading this, I'm kind of marking individual important pieces. If I start with 25,000, that's my P, my principal amount. 500,000 is what I want to end up with. 9% annual interest means R is 0.09. And if it's compounded monthly, that's 12 times per year. So that's our N. So plugging this all in, I have 500,000 equals 25,000 times 1 plus 0.09 over 12 to the 12t. And I want to solve for t. How many years is that going to take? So this is an exponential equation. The first step is to isolate the part with the exponent. So I'm going to start by dividing by 25,000. I get 20 equals, and then I can plug 1 plus 0.09 over 12 into my calculator to see what that is. I get 1.0075. Make sure you use enough decimals. If it's a terminating decimal, I would just use all of them. To the 12t. So 12t is my exponent. Now we're going to change it to log form. So we've isolated the exponential part. Log base 1.0075. So the base of the exponent is the base of our log of 20 equals 12t. Remember, the log equals the exponent. I can plug this in my calculator. Log of 20 divided by log of 1.0075 using my change of base formula. So log of 20, close your parentheses, divided by log of 1.0075. I get 400. Again, use enough decimals, 92697. The more you use, the less likely it is that you're going to end up with a rounding error. Now we need to divide that by 12, and I can just like use what the calculator gave me and just hit divide by 12 on this kind of calculator, which is nice. I get t equals 33.4105, so 411. I want to, let's see, after t years, how long? It didn't tell me to round to any specific years, so I'm just going to leave it like that. So 33.4 years or so, our 25,000 will grow to 500,000 at 9% annual interest. All right, and that's it for today's lesson.